Hello everyone, my name is Suraj Jaiswal and welcome to the second guide for the course entitled Simulation Laboratory course. In this course, we are aiming to design a control algorithm for hydraulically driven crane. And in this particular presentation, I will be mainly giving you instructions about how you can model the hydraulic system. So as you can see in the animation as a sneak peek, this is what we are aiming to model at the end of the simulation work. So let's go ahead and see what are the list of contents we have for the day. So at first I will brief you about a brief introduction, and then what are the modeling of hydraulic actuators comprise of basically the entire circuit, and then what are the parameters there, then some suggestion or tips from my end, and then at the end we will mainly be focusing on the modeling of custom hydraulic component. So if you haven't followed my previous tutorial, it is a humble request that please go ahead and watch tutorial number 6 and 7 from the course Simulation of a Mechatronic Machine. The link will be available in the description of this video, and then it's a good idea to follow this video. So as a brief introduction, as I already told you that our aim is to design a control algorithm for a hydraulically driven crane. So you see on the left on your screen, this is what we have as a real system in our laboratory, and we will be modeling exactly the same thing in as a simulation model. So if I'm blocking anything, so here it has some different number of it is a combination of number of systems such as the mechanical system, such as hydraulic system, and flexibility and control design. So as far as the requirement is concerned, we have already covered the modeling of the mechanical structure, and if you have not followed that video, please go ahead and watch this video. Again, I will make the link available in the description of this video. And then we need to model the hydraulic actuators. So in the modeling of hydraulic actuators, what are the parameters or what are the components that those are required? Very basic components we'll be using. So basically the hydraulic circuit will be a simple hydraulic circuit, and the components will comprise of pump, tank, a directional control valve, and a double acting hydraulic cylinder or actuator. Then modeling of flexibility in structure and modeling of control system will be followed in the upcoming tutorial, so stay tuned for that. And let's go ahead and see the hydraulic circuit. So very brief introduction about the mechanical structure. If you have correctly modeled everything in Simscape multibody, then you will have one body over here which is the pillar. Then there will be another body here which is the lift arm along with the lug and all the necessary components. Then there will be a cylinder and a piston modeled as two separate bodies, and then there is additional body which we will model in Simscape multibody, and then there will be associated joint, and the origin will be at joint 1, which is connecting the pillar and the cylinder. Joint 2 is connecting the pillar and the lift arm. Joint 3 the piston and the lift arm, and joint 4 is connecting the cylinder and the piston, and joint 5 is connecting this additional mass block with the lift arm. What will be these joints? You need to figure that out because it is your job. And the one thing that we can tell you is the overall degree of the freedom of the system would be 1, and you need to see very carefully that you do not have any redundant constraints in the system. So if you go to Simscape multibody and if you go to analysis Simscape or Simscape analysis and then statics viewer, there you can see the degree of freedom of the system and how are the redundant constraints. Make sure that you don't have you do not have any redundant constraints, and the degree of freedom needs to be 1. So based on these two information, you need to figure out that what will be these different joints, what will be their type, either a revolute joint or a spherical joint or a bearing joint. It's your responsibility. So that was a brief introduction of the mechanical structure. Now let's focus on the hydraulic circuit. So across this joint 4, we need to have a hydraulic actuation, and the hydraulic actuation will be provided by this hydraulic circuit, where it has number of components. So what are the components that we have here? We have a variable displacement pressure compensated pump, so basically a variable displacement pump. Then we have a tank, we have a directional control valve, and then we have a double acting hydraulic cylinder. Remember that in tutorial 6 and 7, what we had over there, those were also similar components but of different type. For example, the directional control valve in those tutorials were 3 by 2, whereas in this one we have 3 by 4 directional control valve. In those tutorials we have the hydraulic cylinder as a single acting, but here we have a double acting hydraulic cylinder. And the pump also, there we had a constant pressure source as a pump, but here we have a variable displacement pressure compensated pump. So be very careful while modeling, and I'm very sorry that I'm all the time giving references to the previous tutorial 6 and 7, but please note that those two tutorials are needed to serve as a base in order to model this part of the simulation work. So for that reason, if someone has not followed those tutorials, it is very important that you familiarize yourself with those tutorials and feel comfortable. Then modeling this part of the circuit will be just very easy for you. So the parameters which are already provided to you are, okay, if I'm blocking anything, maybe then I'll try to move. I don't keep a track of that. But anyways, so the parameters that are provided to you for the variable displacement pressure compensated pump, a manufacturer's catalog is provided, and then the model that we will be using. Similarly for the 3 by 4 directional control valve as well. Whereas for connecting hoses, their dimensions and length, so basically the diameter and the length are provided, and similarly for the hydraulic cylinder also the dimensions are provided. Good. But there are some other parameters which are which might not be provided to you in the simulation work, but I have included them in my presentation and in my video. So there are some missing values, for example bulk modulus of oil, the bulk modulus of hydraulic cylinder, or the fluid density, kinematic viscosity, or how you can model the fluid properties in Simscape multibody. So you can find these information useful. So if you know how to model them from tutorial 6 and 7, it would be very easy. So now there are some suggestions and tips that I would like you to be very careful about it, that do allocate enough time in order to model the hydraulic system, because it is the most laborious part of the simulation work. And before doing anything, make sure that you understand all the equations there. So in order to understand the equations, you need to write all the equations using pen and paper, and then try to make sense out of it. Once you understand everything theoretically, then it's a good idea to go ahead and model it. But remember to include these equations in the report, because they are important, so that uh, when I will be reading your report, I would know what is the equation that you have used in order to model certain component, and that is how the scientific reports work. And also explain them in the text. Also list all the parameters that you have used in your case study. and it is highly recommended that follow tutorial 6 and tutorial 7 from the previous course, simulation of a mechatronic machine, because it is very important. So okay, if you haven't started modeling the hydraulic component yet, I would request, or I would suggest you to start modeling using the library component block. So basically, similar way as you have done in tutorial 6, so follow all the ready-made component blocks from the library. For example, you can use a constant pressure source pump, you can use the ready-made directional control valve, but remember 4 by 3, and the double acting hydraulic cylinder. Once everything works fine for you, then you can replace all the ready-made component blocks with your custom hydraulic components one at a time, so that the debugging of your model would be easy, because if there are some discrepancies, then you will be able to figure out, because if you have modeled something as a custom made and it's not working, then you know that the more problem must be in this part of the model. So that is my suggestion so far. But once you have this working model already with the ready-made component blocks, okay, if I'm blocking something, then I would suggest you to go ahead and model the custom hydraulic components. So this part of modeling the pump as a variable displacement pressure compensated pump, I will come to this at the end of this video. Reason being, uh, it is not needed at the moment, because what I would suggest is start modeling with constant pressure source as a pump, and then when everything works fine, then you can replace it with this variable displacement pressure compensated pump. So let's skip this part for the time being. Let's come to the directional control valve. Okay, so the first step in the directional control valve is to understand the directional control valve carefully. In this case, we have a 3 by 4 directional control valve, as you can see. Why 3 by 4? Why is it called like that? So 3, because there are 3 ways. Either this will be engaged, or this will be engaged, or this portion will be engaged. Okay, so for that reason 3. Why 4? 4 means there are 4 ports. For example, P, T, A and B. P is connected to the pump, T is connected to the tank, and A and B are connected to the other part of the circuit. So basically side A of the hydraulic cylinder and side B of the hydraulic cylinder. Okay, and be very careful to understand that this U is basically it serves as a reference spool position. So for example, if this is your directional control valve, what this U does is just the movement of this valve like this in either direction. Yes, and make sure that there are these ports are always at the same location. So A, B, P and T are always at the same location, but this directional control valve moves like U greater than 0, or U equal to 0, or U less than 0. Okay, so this is how the movement is done. So accordingly, we say let's this portion is U greater than 0 and this portion is U less than 0, and in the middle U is equal to 0. So basically the spool position, relative spool position. So first understand what is the functionality of this directional control valve, and how then what are the governing equations. So the functionality of a directional control valve is just to change the direction of the flow, right? That's why it's called directional control valve. So basically it can make a connection from port P to port A and port B to port T, or it can make a connection to from port P to port B and port A to port T if this one is engaged, or no connection at all. So basically changing the direction of the flow. Once you know this functionality, then what is actually or what might be the equation which is governing this directional control valve? Of course, if it is changing the direction of the flow, then the volume flow rate, or the how the fluid is flowing across the directional control valve is what I would be interested in, because that's the ultimate functionality. Like if you if you have some flow at port P, and then you need to figure out what is the flow at port A, or if you have some pressure at port P, and then you need to figure out what is the pressure uh, flow at port A. And why there's a flow rate? Because whenever there's a pressure difference, so fluid flows only when there is a pressure difference, because if there is no pressure difference, then the fluid will remain as it is still. But since there will always be some pressure difference between across the port, and that's why there will be flow. So what is the equation that is governing this flow? It is this equation: Q is equal to CV into U into signum of delta P square root of mod of delta P. Signum function is basically giving the sign of this delta P, and delta P is the pressure across the valve. Okay, Q is the flow rate through the valve, and CV is a semi-empirical flow rate constant of the valves, which can be procured from the manufacturer's catalog. So basically, what kind of valve we are using, accordingly it will have some CV value associated to it. Whereas this U, which is the relative spool position, you need to determine based on some input signal. And suppose you are giving some input reference voltage signal as UN, then using this differential equation, you can figure out what is will be U in this equation. So basically U is coming from this differential equation here, which you need to solve as well. And here is a time constant, which is again a parameter which is dependent upon what kind of valve you are using. So this tau and this CV needs to be figured out from the manufacturer's catalog. Okay, and for your case, you can take it as shown in tutorial 6 or tutorial 7, because later it will be provided from the actual measurements, from what is the value of U in that we will be using in the actual laboratory setup. You will be using exactly the same value, and we will provide you, so do not worry about that. So just this equation is very careful, because this equation is what is defining the flow across the directional control valve. And in the next slide I will show you how we use this equation to model all the different equations for our case, and of course this is needed as well. So let's come to the modeling part. For modeling a custom hydraulic component, you need to model, or you need to code your equations and everything in a .ssc file, which you can download it from the comment section of this video. But how to model them using those .ssc file, again tutorial 6 and 7 will be your guide for that. If you already know how to model that from those two videos, from those two tutorials 6 and 7, then the information provided in this slide will help you. But just let me explain you how. So let me use a sniping tool so that I can show you exactly the same things. Yes. So when we model a hydraulic a directional control valve, we need to define some nodes in our .ssc file. In this case, the ports P, T, A and B are modeled as hydraulic nodes, where port P and T can be on one side of your block, SimScape block that you are defining. For example, let's say PT can be on a left side and AB can be on the right side. So those right side and left side are just for representation point of view, but it is crucial that you give which side, or else the code will not know which side the port should be available. Then, as I already told you, that you need to provide some input value to your model, which will be U in, so the reference voltage signal, and as a result of which you will have an output relative spool position. So this output we will be actually plotting that, and that's why we are interested in this output. And also this output will be used in your equation over here. Okay, what are the parameters? As I already told you, so the semi-empirical flow rate constant and tau are the ones which can be procured from manufacturer's catalog. I will brief you how you can do that. So first let me explain the equations and the remaining part, and then I can do that. And what are the variables needed? So in your case, u is greater than 0 for this part, and u is less than 0 for this part, and u is equal to 0 in the middle. Or you can take the other way round as well. It is up to you how you are defining this u greater than 0 or less than 0, or for which part. Okay, but there needs to be some reference point, and then u greater than less than 0. Okay, so suppose when u is greater than 0, then port P is connected to port A and port B is connected to port T. So there will be some flow across these connected ports. So why there will be flow? Because there will be pressure difference associated to it. So let's define variables that are representing the pressure difference. So let's define a variable PA, which is actually defining this pressure difference between port P and port A, and the other variable PBT, which is defining the pressure difference between port B and port T. So for these two associated pressure difference, there will be associated flow through those ports. So basically a flow from port A to from port P to port A, there will be this flow, and then there will be another flow from port B to port T, which we call it variable as QBT. So this is when u is greater than 0. Similarly, when u is less than 0, you will have associated pressure difference, which let's define it using a variable. Let's define it PB, which is basically pressure between port P and pressure between port B, and then PAT, which is defining pressure between port A to pressure between port T. Because you know, when u is less than 0, port P is connected to port B and port A is connected to port T. That's why we define pressure difference like this. And for these pressure difference, there will be associated flow, which will be flow from port P to port B, and then flow from port A to port T. So this is very simple, coming from just if you know the connections properly, you know you have the pressure difference across the port as a variable, then there will be associated flow for that pressure difference across that particular port. So in any connection, there are two I mean in any three connections there will be 4 ports connected, basically port P to port A and B to T, or port P to B and A to T. Yeah, port P to B and A to T. Okay, so once these are connected, then you need to also define branches if you follow the previous tutorial number 7. So how are the branching done? What is this QPA? How will your code know? So basically QPA is defining the flow from port P to port A, correct? And variable QBT is defining the flow from port B to port T. Similarly, QPB is defining the flow from port P to port B, and QAT is defining the flow from port A to port T. So when these branches are like clear to you, then you need to write the equations carefully. And how you can write the equations? You can write the equations using this equation that I already provided you. So the equation for you will be this one, that's clear. But for the equation for different variables that you have defined, like different flow rate variables and the associated pressure, will be based on this particular equation. So basically flow rate is equal to CV into U into sine of this change in pressure and square root of mod change in pressure. Okay, so when U is greater than 0, so this case I'm talking about, this one, when U is greater than 0, this one, then P is connected to A and B is connected to T, correct? So what will be the flow rate across PA? Flow rate across PA will be CV into U into signum of pressure difference across them. So pressure difference is the variable which you have defined for that. So basically PP minus PA and square root of that modulus of that variable for the pressure difference across P and A. Similarly, flow from port B to port T, which is QBT, is CV into U into signum of the variable associated to the pressure difference across these two ports. So basically PB minus PT and square root of modulus of that pressure difference variable. And what will be the flow between, so there are two other flows as well. So basically flow from P to B and flow from A to T, they will be 0 because they are not connected when U is greater than 0, correct? This needs to be very clear. And now when U is equal to 0, then all the four flow rates will be 0 because there is no connection at all. And when U will be less than 0, in that case, okay, if I'm blocking anything, so sorry. I hope I did not block anything in the previous slide. Oh yes. So I hope I'm not blocking now. Yes. And when U is less than 0, then the flow between P and A will be 0, B and T will be 0 because they are not connected, but P and B are connected and A and T are connected here in this one. So for that case, you need for these two variables, when U is less than 0, you need to define their equation using the previous equation which I have showed here, and you need to assign the associated pressure difference and the associated variable to that. So obviously I have just provided as an example for U greater than 0. You need to write the equations for yourself for U equal to 0 and U less than 0, because we expect you to do that already and understand these equations carefully. So okay, if you have understood this part correctly, then just from the theoretical point of view, when you are trying to solve something, when you have some unknowns that needs to be solved, then you need to have equal number of equations. The number of unknowns should match the number of equations, right? So what are the unknowns we have here? So basically the variable counts. So the unknowns, by the way, this CV and tau are not the unknowns. They are actually parameters whose value are already provided to you, but in a manufacturer's catalog. So you need to figure out for yourself. But the variables that I'm talking about are the variables which is actually in a dynamic system, the variables which keeps changing with time, and those are dynamic parameters, you can say, or the variables, and we don't know their value, and that's what we need to solve as a function of time. So what are the unknowns? This variable here, pp minus pa, we call it just one variable as pa. When you follow tutorial 7 and see there, I have defined accordingly. Then there is another variable for this part, another variable for this, another for this, and then these 4. So total 8 variables here which are unknown. Then there is one another unknown, which is the output. We don't know that because that also is changing with time, and we need to solve using some equation, right? So there are total 9 unknowns. Now let's see, do we really have 9 equations? If yes, then theoretically we have solved the problem. All we need to do is just code it. So see this part. In either of the engagement, whether u is greater than 0 or u is equal to 0 or u is less than 0, there will be 4 equations associated to it. These 4 flow rate, volume flow rates. So there are 4 equations. Okay. Then there is this spool position equation, first order differential equation. So a total of 5 equations. There are 4 more equations, which are these 4 equations over here. So if you follow the 7th tutorial, you will understand it carefully. When we are defining this variable PPA, it is actually representing the pressure difference between port P and port A. So the variable associated to this difference is another equation, right? So PPA is equal to P. So let me write here. So this is what I'm trying to explain. I'm defining it as a variable PA. Excuse me for my handwriting. That is equal to pressure between port P minus pressure between port A. Yes. Similarly, there will be 4 equations from this part. So 4 here, 1 over here, and then another 4 here. So a total of 9 equations you have already. So 9 unknowns, 9 equations, you can solve it very easily. So that's all for modeling the custom hydraulic component, which is directional control valve. Please follow tutorial 7 and then follow this one. It will be very easy for you because it's basically the process remains the same. It is just you are implementing more equations and more unknowns and more variables, whatever, but the process remains the same. That's why I'm asking you to follow tutorial 7 in detail and then follow this one. Now before we move on to understand understand the hydraulic actuator and model it as a custom hydraulic component, let's first understand our hydraulic circuit. So as you know, in this course we follow lumped fluid theory to model the hydraulic circuit, correct? This is kind of a modeling approach which has been followed in research work a lot. So with this you can model any hydraulic circuit very easily. And what does this theory says? In this theory, the entire hydraulic circuit is divided into discrete volumes. We also call it as hydraulic control volumes. And then in that particular volume, there will be some associated pressure, some associated effective bulk modulus, and that's it. Then you will be able to define all the parameters, for example the flow rate, the pressure, the effective bulk modulus you already know, volume you already know. So if you see your entire hydraulic circuit, so this is we consider as section 1, where you have a pump and a hose connecting to it. So why this entire thing is section 1? Because the hoses also has contribution in your system. It can introduce extra stiffness into your system. If the hoses are too small, then there will be some stiffness. If the hoses are too long in length, then there will be certain volume of fluid inside the hoses, and you should consider them because everything will affect to the pressure and the volume and the effective bulk modulus, of course. So this part of the circuit is considered as section 1, where it has associated pressure, effective bulk modulus and volume. This part of the circuit where, so this is the piston side of the hydraulic actuator and this is the piston rod side. So this section 2 comprises of piston side of the hydraulic actuator along with the hoses connecting that particular side with the directional control valve. So, and we say it P2, B, E2, V2, so section 2 basically. And there will be another section, third section, which comprises of the piston rod side of the hydraulic actuator and the connecting hoses, which is connecting that side of the hydraulic actuator with the directional control valve, and it will have associated pressure, effective bulk modulus and volumes. So now if you have understood this part carefully, we will move on to modeling the hydraulic component. Why this part is important? Because when you will be modeling the hydraulic actuator, you will be actually modeling these two hoses as well, because you will model this part. Basically you will model this part, mo model section 2 and section 3. So that's why this understanding was needed. So now let's move on to the custom hydraulic component entitled double acting hydraulic actuator or cylinder. So how we can model our custom double acting hydraulic actuator or cylinder, you can call it either of them. The first step is to understand the hydraulic actuator. Okay, so in order to understand hydraulic actuator, you see we have a double acting hydraulic actuator and not a single acting hydraulic actuator. In your tutorial 6 and 7 we had single acting hydraulic actuator. So single acting hydraulic actuator means there will be just one port on either end of the cylinder, whereas double acting hydraulic actuator means there will be two ports on both ends of the hydraulic cylinder, and that's why it is named as double acting hydraulic actuator or hydraulic cylinder. Here we have port A and port B. So basically port A is connecting to port A of the directional control valve and port B is connecting to the port B of the directional control valve. Okay. Now there are two sides, as I have already told you, this piston side and piston rod side. Now in order to model this, as I told you, you need volumes, you need effective bulk modulus, and then accordingly you can define the pressures or the volume flow rates. And once you have all three of them, then you can actually sorry, let me repeat again. You need volumes, you need effective bulk modulus of the sections. Then accordingly you can define the pressures or the volume flow rates. Based on these pressures, you can define the force coming from the hydraulic actuator. So that's what we are interested in. The force is coming from the hydraulic actuator, because this force we will feed back to the mechanical structure to across the joint which is connecting the physical cylinder and the piston. So the rigid body cylinder body, so the rigid body cylinder and the rigid body piston and the joint across them. So across that joint we will feed this force coming from the hydraulic actuator. So for the piston side volume, so basically volume in this side, okay, volume in this side of the section. So this side I'm talking about, this section 2, P2, BE2 and V2. This can be if this is and remember this x is actually the piston position and x dot is the piston velocity. So and the length of the cylinder is L. So what is the volume on this end? Is volume will be area of this part of the cylinder into x, and what is the volume in this connecting hoses is V naught. Now just imagine when x is 0 and this is completely in the downward position, then volume in section 2 is mainly the volume of the connecting hoses, and that's what it has been written in the equation here. Whereas when the volume in this part of the cylinder is there and it is greater than the volume of the dead volume of the dead volume, which the dead volume is basically the volume of the connecting the volume inside the connecting hoses, basically the volume of the fluid inside the connecting hoses. So if the volume in this part of the piston, so piston side of the hydraulic cylinder, if the volume in this part is greater than the volume of the hydraulics inside the piston, then we can completely say the volume of section 2 is basically A1 into X. What is A1 into X? A1 into X is the volume in this side of the cylinder. A1 is the area and X is the piston position. So the volume is A1 into X. You can also model it as A1X plus V0 to be very careful, but usually V0s are pretty small, so that will not have much of an effect here. Similarly, for the other side, so basically for this section 3, you can have so basically V3, that what we are talking about, which I have called it VB here. So don't get confused with this V3 and V2 here, because V2 is actually VA and V3 is actually VB. So just do not get confused with the notations, but try to understand the logic. Similarly, when this portion here is connecting with the connecting hoses, the length will be of this piston rod side will be L minus X. Okay, and accordingly, following the similar logic, you can formulate the equation here. Of course, you can add V0 in when this A2 into L minus X is greater than V0, but V0 is usually very small and it will not make much of a difference. So you figure out what will be the volumes. Very good. Once you figure out the volumes, the next step is to figure out what will be the effective bulk modulus. But remember, in these volumes, this X is basically the piston position, and this data is coming as an input from your cylinder, from your joint, because from your rigid multi-body cylinder and a piston and a joint between them, you can figure out, or you can use a sensor there, and you can figure out what is the position of the piston there in your actual physical system, and using that input you can input it here in your hydraulic circuit, and then you can have the associated volume and obviously the effective bulk modulus, which is dependent on volume. So in order to calculate effective bulk modulus, it can be calculated as per the lecture note. So basically considering the effective bulk modulus of all the parts of that particular section. So let's say we are talking about section 2. So in this part, what are the components that is contributing? So basically we have this part of the hydraulic cylinder where we have certain volume, and the effective the bulk modulus of the material of the hydraulic cylinder is provided to you. Okay, then this connecting hose, it has certain volume, and the bulk modulus of this connecting hose needs to be determined. I have provided the equation, I'll go to that. And then there is fluid inside this, so basically oil, and that oil also has certain not effective but bulk modulus. Okay, so these are the three components that is comprising section 2. Similarly, section 3 also has three components that is describing section 3 for the effective bulk modulus. Okay, so accordingly you have bulk modulus of oil here, then the bulk modulus of the hoses, and the bulk modulus of the cylinder, and associated volume of the cylinder, associated volume of the hoses, and VT is actually VH plus VC. If you follow the hydraulic lecture note, I will make that available for you in Moodle. For the bulk modulus of hoses, you can use this expression here. and using this expression where pH is the pressure in the hose, so basically the pressure in this part of the circuit or this part of the circuit, accordingly which side you are designing. I hope I did not block anything. Yeah, I'm so sorry. I need to be very careful with that. So maybe you can see now everything. Just hose written at the end. Okay, so once you figured out the volume in both the sections, effective bulk modulus in both the sections of the hydraulic circuit, then you can use lump fluid theory to calculate either the pressure or the flow rate. So if you follow the standard lump fluid theory, it's always written as P dot, like you just rearrange these terms and then write P dot as the other terms. But in this case, we are using volume flow rate because that's how the entire circuit is connected, using the volume flow rate of the fluid, correct? So that's why using this equation we can formulate the volume flow rate in either ends of the hydraulic section or in either ends of the cylinder. So basically flow rate in this part will be uh, the associated pressure, let's say P dot A, then VA by BE2, then A, this A, basically A1 into X dot, and accordingly you can formulate it for the other part as well. Okay, so once you have done that, well and good, you have formulated most of the parts carefully. Just a note, like in this one you have a n into x dot, whereas in the other one you will have, I think, a 2 into l minus x dot or minus x dot. Just see this carefully, like if you write the equations, you will figure that out yourself. So now once you have the pressures already, or the flow rate, and basically calculating the pressure, once you have the pressures already available, I mean you have solved it, then using this pressure you can estimate or you can compute the forces that is coming out of this hydraulic actuator. How you can do that is basically force in this part, which is let's say uh, A1 into PA, minus force in this part is PB into A2, and then this part of the equation is associated to the friction force, so having some efficiency there, and then modulus of this force difference from the pressure into the piston velocity. So normally friction models can be improved version as well, but here we have a pressure and a velocity dependent friction model. Since it's pressure dependent and pressure fluctuates, so friction model fluctuates, so the force fluctuate and your entire system will fluctuate, as it was happening even in your last simulation work. So just for your note that it's the friction model which is affecting that fluctuation. So using this simple basically Newton's second law, what we have written here, and we can estimate this force, and obviously the friction is acting in the opposite direction, that's why there's a negative sign. Okay, so once you have done that, well and good, you have understood all the equations carefully. So if you see all these equations, what are the parameters that are like we require? V naught, A1, A2, then the bulk modulus B naught or B H B C. These are the parameters actually you can figure out, right? Just a minute. So bulk modulus of, okay, bulk modulus of the hose you need to calculate, whereas bulk modulus of oil and bulk modulus of cylinder, it's provided to you. So okay, and the efficiency here. Okay, so once you have understood these equations carefully, let's go ahead and start doing the coding and how we can do that. But before that, there is something which I just realized will be we need to put here as a correction. Is this VH is volume of the hose, volume of the cylinder, volume bulk modulus of hose. Okay, B naught and BC. So just a minute, and I need to do some corrections here. So every time I explain this, I do some corrections. Just a minute. Okay, I think I'm done. Okay, so I have just added this B naught and BC because I realized those are also the parameters that you need to figure out, and their unit will be Pascal, I think. Right. So in order to model your double acting hydraulic cylinder using uh, .ssc file, you need to have ports there. So let me copy this figure so that we are able to understand it carefully. So you need to model the ports as hydraulic nodes, which can be on right side, for example. So if you follow tutorial 7, you'll understand what is this right side and left side. Do not worry about that. So basically right side is on this end, and then we will have some inputs, basically the piston position and the piston velocity, which can be on the left end, and it is coming from the hydraulic from the mechanical structure. So basically sensing the position of the piston and the velocity using some sensor, and then taking those values as the input for your block here. Then as an output, you know that we want the force which is coming from the hydraulic actuator, because that is what we are interested in. That's why we have modeled the entire hydraulic system. And remember that you cannot like once you have this force, you need to input that into your mechanical structure across the joint. And how you can do that? You cannot directly do it because the force output is a signal and cannot be connected directly to the physical system. You need to use external force and torque and PS gain blocks. So please follow tutorial 7. I have already given a brief demonstration over there how we can do that. So please follow that one. So what are the parameters that are required for modeling this part? So basically the area on both sides of the cylinder, then the dead volume, basically volume of the hoses, then the bulk modulus of the oil, bulk modulus of the cylinder, then the efficiency of the cylinder. These are the values. Those are parameters that those needs to be either figured out from the manufacturer's catalog or are already provided to you. So those are actually already provided, so you don't need to figure out from there is no catalog, manufacturer's catalog for that. Okay, so once you have understood that part, understand the variables that are needed. So the variables that are needed are the pressure difference in this part of the circuit, so basically PA, and the associated flow, which is QA. Similarly, there is the pressure across in this part of the circuit, which is PB, and the associated flow is QB. And in the process of calculating pressures or the flow rate, you need the effective bulk modulus as well, and you can model it as a variable. Why as a variable? Because if okay, I hope I did not block anything here. Yeah, so if you see this equation here, it is actually changing with time. Reason being, they are dependent on either the pressure here, or the volumes are dependent on the piston position, and piston position is changing with time, so the volumes are changing with time, and the effective bulk modulus are also changing with time. So for that reason they are also variables. And the branches, how is the branching done? If you followed the 7th tutorial, then you will understand you need to even model the branches there. And how's the branching done? So basically QA is defining the flow from port A to nothing, because this is blocked here, there is nothing and it's not going anywhere, right? Similarly, QB is defining the flow from port B to nothing, because that flow cannot go anywhere, only the force can be transmitted, right? But flow is just there. So once you have understood this part carefully, then you need to figure out, write all the equations. So all the equations I have already provided you here. You need to just figure out for individual sections, write them using pen and paper. This part remains the same as tutorial 7. I mean, the volume equation can be put between let and in statement, reference tutorial 7. Then it utilizes previous volume, please follow tutorial 7. And then in calculation of hydraulic force, we divide this velocity, piston velocity, with 1 meter per second, because if you see carefully from unit point of view, force is in Newton, this pressure into area is also in Newton, this is Newton, this is dimensionless, whereas this x dot is meter per second. So subtracting a Newton with Newton meter per second is not making sense, right? So that's why we divide it by 1 meter per second, and then dimension wise it becomes consistent, and then we can do that. So now note, like theoretically we want to solve, I want to solve it theoretically first, then I would like to code it. So I will see the number of unknowns and the number of equations. Both of them must be equal. So what are the number of unknowns? First, this variable counts. So basically 1, 2, 3, 4, 5, 6, and then one output. Correct? So a total of 7. Let me see, do we have 7 equations? So for the force we have one equation, well and good. We need 6 more equations. So this volume flow rate will be there for either sections of for both sections of the hydraulic actuator. So there will be 2 equations from this one equation, because there are 2 sections. So 3. Then you have so the volume equations here. So either this volume equation have one equation, this one has also one equation, effective one equation, because the conditioning might differ, but at any time there is just one equation associated to it. So equation 4, equation 5. Then this effective bulk modulus, this one equation needs to be applied to both sides. So accordingly you have 2 more equations. So basically 6 and 7 are also incorporated here. So a total of 7 unknowns, 7 equations. So theoretically we have solved this problem. Well and good. So start with the coding of these 2 parts, and when everything works fine, then you can go ahead and model the pump. So now let's go back to the pump modeling. So yes, before going to the pump modeling, before going to the pump modeling, so this pump is a variable displacement pressure compensated pump, but it also has some hydraulic hose with it. connecting hose with it. So we need to take that into account as well. So how you can model the pump? So till now you were using constant pressure source pump, and when everything is working fine, all the other components are working fine. Now you need to change that to variable displacement pressure compensated pump block in Simscape multibody. So the path, you can find it here. For example, go to library, Simscape, fluids, hydraulics, then pumps and motors, and you can find this block there. This is how it looks. Okay, so in order to understand what is happening inside this pump, it is highly recommended that you follow this link. Description will be provided in the description of this video. I don't know why is it not opening. Okay, now it's open. So this link here, so basically it's describing this block and what are the different equations governing them. Try to make sense out of it, and when you write them in the report, try to explain as much as possible and whatever you have understood. So that's what we are testing. Like we have introduced a new block to you, and it's your responsibility to figure out the governing equations and trying to make sense out of it. So once you have read that and read all the equations, carefully note that this is how the block looks like, and you need to figure out all the values from the catalog. So I will at the end I will show you briefly how to take care of the catalogs. So these values marked in oranges needs to be figured out from the catalog, and the model is provided, whereas the green ones are the already provided, I think, in the beginning of this video where I introduced the parameters. So if I block anything, so if you read the link carefully, if you read this link carefully, you see the pressure here is uh, P set plus P regulation. So basically this, it's a summation of setting pressure and the regulation pressure range over here, these two. Setting pressure, I think it's the one, the student specific values are already provided to you, which is approximately like 150 bar plus minus different for other students. Usually for factory setting, these setting pressures are 50 bar, so just try the student specific value. I think that will work. And the regulation pressure range you need to figure out from the catalog. Okay, about this nominal angular velocity, one can assume that constant input shaft rotation speed is being applied, which is 1500 rpm. So basically assuming we have an ideal angular velocity source for our pump. Once you have modeled the pump carefully, you need to also incorporate the pump hose modeling, right? So I would suggest you to look for the source code of this constant volume hydraulics chamber. So if I go to my MATLAB and type smnew, it will take a while. Let it open. So we will see the pressure source code of this one, and at the same time we will also refer to this link where all the equations that are needed in order to model that source code are provided here. For example, all the equations are here for this particular component, and the same equations are modeled in the source code. So if you search, for example, constant volume, let me show all the names here. So if we search constant volume hydraulic chamber, double click this, click source code. This is basically a .ssc file, as you can see, and how it has modeled using the equations that are given in this website. You need to make a sense of out of it, and then accordingly you need to define similar component for taking care of the pump hose modeling. Okay, so this is your responsibility, and the reason for doing this is basically we want, like so far we have provided almost everything that you need to model the system, whereas this one particular component is something which we have not given you the detailed information. So it's your responsibility as a student that you need to figure out yourself and see what, and we would like to see what you can figure out, and maybe I can learn something from you. So I think once you have done all of this, then at the end you need to carry out the find the static equilibrium. You can do that using steady state manager. So in order to understand the procedures of steady state manager, follow tutorial 6 from 50 minutes onward and tutorial 7 from 1 hour 9 minutes onward. The links will be provided in the email of this description. So if you follow tutorial 7, when you were doing steady state manager, you were just trying to figure out the value of the pressure on one side of the cylinder, because you had single acting cylinder there. In the present simulation work, you have a double acting hydraulic cylinder, and for that reason you need to figure out the pressures on both sides of the hydraulic actuator using this steady state manager. And also remember that the default tolerances and iteration count inside the trim options when you follow the steady state manager might not be enough to find perfect static equilibrium. So you might have to play around with those values there. But I think the values which are there by default might work for you. So just try to play around with those values there. And also note that when you are unable to execute the steady state manager and you decided, okay, you want to figure out the values manually, and then you manually put those value into your system, in that case what happens is you have those values manually modeled into your system, and at the same time you might have some priority conditions for other parameters such as the joint position. You have some high priorities there. The simulation will end up in a mess because the model will try to have will try to fulfill those high priority first, rather than considering what are the values provided to you. So be very careful with these things, and the suggestion is that you follow steady state manager and do the allocation of those values automatically from there, following tutorial 6 and 7 as already told you. So I think from the presentation point of view that is all, but there is something which I told you that I will help you to figure out the or how to read the manufacturer's catalog. So okay, so first the directional control valve. In the directional control valve, the parameters such as CV and tau needs to figured out from the manufacturer's catalog. Okay, first understand how you can obtain these values or how you can calculate these values in theory. So if you follow this hydraulic lecture note from the course, let me take you to this part of throttle valve. Where is it? Yes, this part. So this particular example, if you see carefully in this particular example, how uh, they have calculated the semi-empirical flow rate coefficient. They have used basically from your equation they have not considered u. So avoid u for the moment, and based on the nominal flow rate and the associated pressure difference, you can calculate CV, correct? And then in order to calculate tau, this is what they have used. This is the equation if you read them in carefully. So basically the frequency at minus 45 degree phase shift from the board diagram. So this is how you calculate CV and tau. So now you need to figure out these parameters, so basically these values from your catalog. Let's see the catalog. If you follow this catalog, you can see that it is quite lengthy, and if you try to make sense out of everything, you will be confused. So uh, like I, as an engineer, I always try to first figure out my requirements, then I see what are the things needed in those requirements, and then I try to find those things from the material provided to me. That is the most simplest approach, I would say. So as you already know, like for CV we need nominal flow, we need the associated pressure difference, and we have also provided you the model, the code that we are which directional control valve we are using. I think these are the codes. So suppose maybe this is your code, I'm not sure. So for this code I already know Q nominal, so the nominal pressure flow rate I know, delta P, so the pressure difference I also know, so I can easily calculate CV, correct? Similarly for time constant tau, let me see a board diagram. This is a board diagram, well and good. So using this board diagram and at a minus 45 degree frequency phase shift, which is minus 45 phase, so minus 45 would be this one and 100% u this one, something like this. So this is the value that I'm looking for. So this is how you read values from the manufacturer's catalog for a valve. Okay, so once you read them, you can easily figure out the CV and tau. I should have not provided you these information, but as a engineer or as a student, I know these things nobody teach you, and it's very difficult to figure out at times. So that's why I thought maybe I should help you here. And okay, now comes the second part, which is modeling this part. So basically figuring out these values for the pump from the manufacturer's catalog, and this is the manufacturer's catalog that we have. It is quite lengthy, so if you try to make sense out of everything, it will be very difficult, I think. But if you are interested, go ahead and read. But if I were you and I was given this task, it is saying that use the data of Parker PV016, and I can already see Parker is a company, so I will search for PV016. When I search, okay, so these are the models that provided. Okay, so on at the very first it's written some technical data. Of course you can search for others as well, but let's see, are these technical data making sense? So if I see this one, what are the things required? Maximum displacement. Oh, maximum displacement is already here, but we be very careful regarding the units. You should be consistent with your units in your hydraulic system. Then the setting pressure, I already told you, I think it's a pressure student specific. Normally factory setting is 50 bar, but for your case we might take it as 150 bar or the student specific value. I would suggest you to take the student specific value. Then the pressure regulation range, you have maximum pressure, minimum pressure, you can calculate from that. Regarding volumetric and total efficiency, you can consider it as 90%, so basically 0.9 or 0.95 as you like. Then nominal pressure is also here, so I can figure that out as well. and that's it. I think all the other values are already given. So this is how you can read, and of course if you are interested you should go ahead and see read all the descriptions under this PV016 and see if you can learn something. And if you find out something new, please comment in the please write your comments in the comment section of this video, because even I would be interested to learn from you. And since that was this pump modeling is something new that we have introduced, so I would also like to learn from you. So I think that's all for today's presentation. uh, I hope I did not block anything here. Yes. So I think that's all from today's presentation. If you have any questions, you can write. So if you are an in-class student, please contact me on my official email address, which is suraj.jaiswal@lut.fi. But if you're following my videos on YouTube, I would highly recommend you to post your questions in the comment section of this video. And if you like this video, please give it a thumbs up and subscribe to my channel. I would really need your support and your likes so that YouTube recommends this video to more number of people, and more number of people can be benefited from the knowledge that I'm sharing. So thank you and have a good day.